what we have here is, and we talked about what a wave was. Everyone recall what a wave is? What is a wave? Wave is essentially you're passing some energy through a system or a phase or a medium, and that medium is essentially which carries that wave through, and a wave is what? Wave was just a disturbance that is carrying that energy, right? So, and then we talked about that wave could either be a pulse or it could be a periodic wave. So a pulse is what? It's a single disturbance, and a periodic wave was what? It's a repetition, right? And then these could be different in nature. So one wave could be disturbing the particles of the medium, and they would move perpendicular to the direction of wave travel, which was known as transverse wave. And then the other one was that the particles would travel along the direction of the wave or parallel to the direction of the wave, so they would oscillate kind of around that axis, and that was known as a longitudinal wave. Now what we talked about is that in most cases, so when we're talking very small amplitude sea waves or ocean waves could be known as a longitudinal wave. So again, the example of a boat on a jetty comes into mind, where if you've got small waves, the boat wouldn't really move, but it would just oscillate up and down as the wave passes through. On the other hand, for a longitudinal wave, what was happening is, for a longitudinal wave, your sound waves are the ones that act like a longitudinal wave, and that what happens is, because of the way energy travels, it would compress one part of the particles and then expand on the other, and so on and so forth. So the particles are moving sort of in this little motion, so they're moving parallel to the direction of the wave, right? So have you ever seen a tuning fork? Right, a tuning fork does what? Tuning fork, once you hit it, it will vibrate. What that does is, that vibration does what? It moves to one side, so it pushes the air particles on one side, and then it goes back beyond its equilibrium position, and then in doing so, it's kind of creating that vacuum, right? So there are less particles when it's moving back to its original position, and then when it's moving forward, it's compressing those air particles again, right? So that's where this compression part comes in, and this expansion part comes in, and this expansion part is known as a rarefaction, right? And we'll talk more about this when we get to our, what do you call it, the sound waves part, because that's all to do with compressions and rarefactions, right? And that concept we'll build more upon. But essentially, a compression is where all the air particles are squished together, and a rarefaction is when they're expanded upon, right? So you've got less particles in a given medium, or a given zone within the medium, right? And then the other stuff that we talked about was, well, what is a wavelength? What is a wavelength? Anyone?
The length between the two crests of a wave.
Yes, the length between the two crests or the two troughs of a wave, right? And essentially what that was, that for one oscillation, one full oscillation, if you were looking at a cosine wave, if you can follow that cursor of mine, what you've got is that during these two peaks, that is equal to one wavelength, and the time taken to cover this one wavelength is going to be the period of a wave, right? And what was the amplitude? Amplitude, well, was the disturbance of the wave, or a peak amplitude from the equilibrium point, right? And those were the key features of what a wave is. So a wave could either be a sine wave, and a sine wave starts from 0, goes all the way, and ends up at a 0 after a full oscillation. So a sine wave will have one peak or one crest and one trough. Cosine wave starts at 1, so it has half of a crest, then a full trough, and then another half a crest during one full oscillation, right? And then using that, we could find what the speed of a wave was, which was simply the product of the frequency and the wavelength, or in other words, the distance traveled divided by the time taken for for one complete oscillation, right? And then we had talked about or implemented all of this in a question setting, right, or in a question format where you had to find what the amplitude was, what the wavelength was, what the frequency was, and what the period of a wave was, right? Were there any questions from this or regarding this question? And this is all to do with what the features of a wave tell you. No? Okay, right, let's move on. So the next thing that we're going to talk about is wave interference, right? So interference is what? It could be a collision. So we talked about collision in our momentum chapter, right? What is a collision? When two objects collide together. We talked about, well, what is inelastic collision, what is a fully elastic collision. An elastic collision was what? Where two objects would collide and they wouldn't deform and then they would move away from each other, right? There would be some transfer of energy and some transfer of momentum, but essentially they wouldn't fuse together. What was a perfectly inelastic collision? That the objects would fuse together after or upon collision, right? In terms of waves, waves are able to collide with each other, and that's what you observe in the ocean, that some waves have a higher amplitude when they're coming towards the beach, and others when one wave is passing back into the sea, and when two waves overlap, either their amplitude would decrease or they would crash into each other. That's what we call, so that when the waves would crash into each other, their amplitude decreases, right? Is that something that you've observed? Right? So when the waves are being reflected off of a wall, they would move back, and if there's an incoming wave, they will collide with each other and then they would crash. But what happens? That one wave still makes it through and the other one still moves back, right? So they're still carrying that energy with them. What essentially is happening is that is known as wave interference. So in waves, what happens is, rather than colliding and deforming, they will pass over. What you see in the medium is that the particles are going to represent what happened in the wave. So if two waves with different amplitudes or different different phases would collide with each other, their amplitudes would add up and create sort of a combined amplitude. And that combined amplitude could be less than the incident wave, or it could be more than the incident wave. It depends how out of sync they are. So if they're in sync, you would usually get constructive interference, or you would get a destructive interference. Now it depends how, if they're in sync, what I mean by in sync is that their peaks are in sync. So when a peak of one wave passes over the peak of the other wave, you have a constructive interference. When a trough of one wave passes through or is in sync with the crest of the other wave, you would have a destructive interference, right? And that's where that little applet that has been posted for you to look through will simulate for you. But essentially, waves don't collide as we did for matter, because they're just transporting energy. They're just using the medium. They don't really lose any information, so they're just going to carry through, and that energy is going to carry forward. There's no sort of interference of the waves in that sense, that the energy isn't lost. The medium particles are going to represent what's happening to them based on that interference, but essentially this is one of those examples where you've got constructive interference. So when two waves are in phase, so right here you've got peak amplitude for one wave and peak amplitude for another wave, and they are matching up together, what you would see is that you would have an increased amplitude, right? So for wave 1 you would have one amplitude, and for wave 2 you would have another amplitude, and they're simply being added together. And this combined amplitude, or this combined, is going to be represented on the physical medium that you're observing at a given point, right? And now, do you understand what waves in phase means? that the crests align and the troughs align with each other when two waves are passing through, right? And this thing is known as where the crests align and the troughs align with each other for two waves. That is known as constructive interference. When we're talking about that the waves are out of phase, that essentially means that the crest of one wave is aligning with the trough of the other wave, right? And what that would create is, so remember, if these are equal amplitude, so this A is equal to this A, essentially, when you've got a trough aligning with a crest, your amplitude would be what? You would get, well, a straight horizontal line resting at 0, because plus A plus negative A would give you a 0, right? And you're just summing those amplitudes up, or adding those amplitudes together. When they're out of phase, because the trough aligned with the crest, what happened is that's you lose all the amplitude, and that's known as, well, destructive interference, right? Because it has done what? It has done what? It has reduced the amplitude of the wave completely, right? Or of the medium. So that's not being represented there. And that's essentially what is happening with your have you ever experienced the noise cancellation features on a headphone? Right? What is that? That noise cancellation feature is essentially doing what? It's taking in the sounds that are around you, right? And sound wave is what? It's a wave, so it can be represented either by a sine or a cosine wave. So it's taking out those, it's measuring that frequency in there, right? And what it does is it produces a signal opposing that frequency that you're hearing. So it's doing destructive interference with that sound wave that you can hear from the outside. And that's why you don't hear any sound from the outside. And that's what noise cancellation features are. Right? And the current ones, in the current generation noise cancellation headphones or earphones, what you see is that there's no sort of external pack. If you go back a few generations for the current for the noise cancellation features, such as on the Bose ones, you would see that it used to have a little pack underneath in the wire, right? I don't know if you've seen those, but that little pack was doing everything for the wave interference. Now everything is built in because technology's getting smaller in size, or they're able to making it compact and pack it into the actual headphones itself. But way back they had to do a separate thing, or a separate device that was wired or hardwired into the actual headphones, right? And again, constructive interference would be what? It might be used in where else could it be used? It might be used in an auditorium, where they're trying to increase some sort of a audible wave signature to make everything loud, right? And we'll talk more about resonance and all of those things, because that's what sound waves are, and that's particular to sound waves. But generally, wave interference is of two types. One is to do with constructive interference, the other one is to do with destructive interference. Constructive interference is what? When two waves are aligning with each other. So the peak or the crests of the wave are aligned with each other. Destructive interference is when they're out of phase or out of sync, and your peak or the crest of one wave aligns with the trough of the other wave. Right? And I believe there is this little simulation here. So the green one is what? It's a normal wave, and the blue one is passing through. So when the two waves are in sync, you get a constructive interference, and this black line is showing you the amplitude or the resulting amplitude of the two waves. So when they're out of sync, so the blue one creates a crest over the peak for the green one, what you get to observe is a flat line, or there's no amplitude being observed, and that's the destructive interference, right? I don't think these simulations will work in the PDF file. do you all have access to PowerPoint? No.
Yes.
Okay, what I can do is I'll add this to the presentation, so the PowerPoint will be there. So if you have access to PowerPoint, you could use it, and these simulations should work for you. Right? Otherwise, I'll try to see if I can just post these or cut these snippets out and post them on Classroom by themselves. I have not done that before, so I don't know if I'll be able to do that. But I'll try my best. Right, so after wave interference, we talked about wave reflection. Right, so one example that we were talking about is ocean waves. What happens to ocean waves once they collide with the beach? Do they return? Yes or no? Right, or when you slosh water in the bathtub, what happens? When it hits the walls of the bathtub, it sloshes back, right? And what's happening there is that sloshing effect is doing what? You're exciting the water, or you're adding energy, or you're giving energy to the water inside the bathtub. When it hits the wall, that energy is transferred back, and what you get is a wave reflection. And wave reflection is simply then, well, it's the reflection of the wave, so it's the transfer of energy back to the entire system. Now it happens in air as well. So let's think about an example. Since we're talking about mediums, well, a bathtub is an example of a denser medium. So a bathtub is made out of a solid material, so that is its denser material compared to the water itself. Right? So what happens is when you slosh the water through, it will hit and it will come back. Right? And that's the one wave being reflected. That's one way of that reflection. The other thing is, let's see, can you hear sound underwater? Right? But the sound changes more or less when the person goes underwater. So in your movies or films or all those things, you could observe that during, well, I'd rather say torture sequences, but whatnot. Essentially what is happening to the sound wave is through the air, it's traveling at a different velocity, different pitch. Once it hits the water, because the medium has changed, your sound changes as well. Right, so the pitch drowns out and your speed is different, and essentially what is happening is that since the wave passes through to a different medium, the properties change for that medium and the wave travels differently, right? So and then if you remove the audible sound from the water, so you can test this if you've got a waterproof phone, you can play sound, you can submerge your phone into water, or submerge your phone into water and then move it out. You'll see how the voice or the sound changes, and that's essentially because the waves are coming from two different mediums, or one's traveling in air and then the other one's in water. So the pitch, you'll hear a different pitch essentially, but that's all due to the medium that the sound is traveling in, right? So one way to do it is a fixed end reflection. What was a fixed end reflection? That you've got a denser or a rigid medium. So for example, a solid, right? So when we're talking about water wave hitting a beach or your end of the bathtub, you're going to get a reflection, but that reflection is going to be, more importantly, well, what's going to happen to the wave is, if you've got a crest coming in, upon reflection, that crest will change into a trough, right? When we talk about, and that's known as fixed end reflection, when the wave hits a more rigid medium, what happens afterwards is that during the open end reflection, when the wave is moving from a denser medium to a less dense medium, right? So for example, a wave coming from water to your air, you've got open end reflections. And open end reflection is what? The wave will come in, it will lose some of the energy, and then it will be reflected back, but it will reflect back with the crest coming back in, not the trough. So that's the only difference there. And I believe that's one of those examples. So what happens here is that you've got a fixed end reflection. Fixed end reflection was what? That you have a higher density medium, right? And what happens is that the wave comes through here and then it is reflected back, but it's reflected back with a, or sort of out of sync, right? You'll get it for a crest, you'll get a trough. Part of that energy passes through to the higher density medium. When the opposite is happening, what happens is that's known as an open-end reflection, and the wave will still travel through, and it will travel through in the same phase. It won't be out of phase, right? Remember, phase was what? If they're in phase to each other, the crest is doing what? The crests will align with each other. If they're out of phase, the crest will align with the trough of the wave. Right? Yes or no? Okay. So, the next thing that we're going to talk about today is a standing wave. Now, in cases where you may be able to simulate, if you were to pluck a guitar string or something, that the waves would appear that they are, that the wave isn't moving. It's remaining in place. And the way to do it is, or that's where that zero displacement part comes in, that the wave is, or the particles are oscillating on their position, or perfectly oscillating upon their position. And in order to do that, well, what you have to do is you'll have to clamp or fix both ends of the string and then initiate a wave. But you have to initiate a wave in such a way that your constructive and destructive interferences, or the waves, have to be in sync with each other. But in order to do that, you have to make sure that, well, since we've talked about all the wave features, there are two more features that I'm going to introduce. One is a node and the other one's an antinode. Node is the location of the wave where you've got zero amplitude, right? Or minimum amplitude. And amplitude was what? Amplitude is your maximum displacement from your equilibrium position. Antinodes are locations where you get maximum amplitude. Now in this case, what this wave is telling you, that there are two waves passing through. One may be a reflection or whatnot, but what's happening is that because they're kind of in sync, your wave, or this black line, is oscillating about its position. It's not moving. It appears not to be moving. The blue and the red waves they may seem moving to you, but everything else is, or the actual particle line, or this piece of string which is represented by the black line, that's not going to move, right? Or it's just going to oscillate about its position. And where those amplitude doesn't change, that is known as the node location. And where your amplitude changes to the maximum, these are your antinodes, right? And the way that you could simulate this is by, if you have a piece of string with length L, well, you have to create nodes on the two fixed ends. And one way to do it, or the only way you could possibly create this, is by having a wavelength which is twice the length of the string, or the wavelength equals to the length of the string, or 2/3 of the length. What that essentially means is that in this case you've got a complete wave, or your wavelength is equal to the length of the string. And I don't know how to pause this animation here, but this one string is creating half a wavelength, or half the length of the string. So one crest is, what is one full wavelength? What is one full wavelength? For a wave, anyone?
Isn't it like the length of like the crest or whatever? Like the crests?
It's the length, or it's the combined length of a crest and a trough, right? So a full sine wave will give you one wavelength. Now in this simulation, there's no way to pause this animation, but essentially what is happening here is that you've got half a wavelength here because it's only the crest is showing, right? In this case, you've got both crest and trough. That was a full wavelength. And in the other case, you've got 3/2 of the wavelength because you had 1/2 waves. But essentially, you're trying to clamp the string down and you're trying to pluck it or create a simulate the standing wave by creating nodes on the two corners or two ends. And there are multiple factors. It's not only these 3 wavelengths, it could be more as well, right? So it could be 5/3L and all of those things, right? So essentially, when you're able to create nodes on the ends of the corner, you're going to get a standing wave, and that's where the simulation comes in, and you can watch that as well, right? And let's just stop here, and the next time we come in, we're going to start talking about diffraction and whatnot. The in-class assignment that's been posted for you, that does not include the diffraction part. That's what we were going to talk about next. But you should be able to solve it based on the information that we've discussed. You should be able to solve those 4 questions, right? And if you've got any questions, there again, this is more of a conceptual based physics part where you don't have a lot of equations now. The equations will come in when we're going to start talking about sound waves and light waves, and you've got magnification factors and whatnot. But right now, it's more of a concept building exercise. That's a lot more theoretical than what we've been dealing with so far, right? And if I find any more good resources, I've been trying to find some, I haven't been able to, but once I find them, I'll keep on sharing those with you. Since we're on distance learning, I can't really show it to you during class time, right? Or do demonstrations. But that's kind of it for the class today. What I'll be doing tomorrow is I'll be recording the video again, and I'll be posting that. So it should be there around sometime around 11 or 11:30. It should be posted to YouTube, and once you have it, you should be able to solve a few questions. The video tomorrow is going to be starting from diffraction, and we're going to be talking about sound waves and resonance and harmonics. That's on the agenda for tomorrow. And please let me know how this video thing is going. Hopefully we'll be able to be back in person after Thanksgiving. But I'll need your help to make this thing work on the way we're trying to do, for distance learning at least, right? So you have to be kind of proactive and reaching out to me. So if you're not understanding a single thing or a few things, just let me know through email, and then we can talk through. And I'll be happy to arrange office hours or virtual office hours as well. So if you've got questions, then we can do that too. Right? Any questions? No? Well, take care. And I will see you all on Monday. Right? Have a good weekend. Bye-bye.